Okay, hello, this is Dr. D, and this is your first video for Chem 1120, and this is Chapter 6, Intermolecular Forces. So when we talk about intermolecular forces, that inter is the key, as opposed to intra. Just like interstate highway or intrastate highway. Inter means between, intra means within. So intramolecular forces, we can call them that. That's what we dealt with in Gen Chem 1. We take a water molecule like this. The intramolecular forces, these are the covalent bonds that we dealt with, right? That's an intramolecular force. What we're going to deal with now in this chapter is the force between those molecules. So let's take another water molecule here. And the force that holds these water molecules together is the intermolecular force. And there's different types of intermolecular forces we'll talk about in the chapter. But what's nice about it is that these are the forces that explain to you why something like carbon dioxide is a gas at room temperature and why water is a liquid at room temperature. It's the strength of those intermolecular forces. There's enough energy in the room for a room temperature room, whatever, let's say 25 degrees C, to break the intermolecular forces that hold the individual CO2 molecules together. So at room temperature, it's a gas, but water's a liquid. Okay, so that's going to be the difference of why something is a solid, liquid, or gas, these intermolecular forces. That's what's nice about studying this type of material. And that is the difference. Intra is within, inter is between. So the first type of force we're going to talk about, the first one your book introduces, are what's known as either London dispersion forces or just dispersion forces or just London forces. So interactions between, if you will, nonpolar molecules. So these can be just two atoms. They can be any two atoms approaching. Let's just say they're just two neon atoms here approaching each other. And from a quantum mechanical standpoint, we know that there's electrons in these orbitals surrounding the atoms. Well, as they come closer together, it's very possible that an electron here and over here, and I don't want to use location is too much of a descriptive term, but they're in proximity to each other and they're going to repel each other, which could result then in electron shifts within one of those atoms that results in partial negative and partial positive charge. So if electron density in this one is kind of shifted away from this region here as a result of repulsion from here, this now has a partial positive charge and this has a partial negative charge. They can now attract each other. That's the London dispersion force. It's kind of this weak temporary dipole that results. And these are the forces that are present between all molecules. So if someone asks you what types of forces are present between these molecules, London dispersion forces will always be part of your answer. There might be other forces also, but everything experiences London dispersion forces because there are electrons in all substances. And these electrons are subject to these kind of charge density shifts and imbalances that result in these opposite charges attracting each other that we see here. So that is what London dispersion forces is. What London dispersion forces are. And they depend on several things. They depend on the size of the molecule and the shapes of the molecules. Just looking at molar mass, if you will, the size of these are just your halogen diatoms. And we're going to focus on these right here. And remember how I said these intermolecular forces explain why certain things are solids, liquids, and gases at room temperature or given any given temperature. Well, you should know from Gen Chem 1 that this is a gas, this is a gas, this is a liquid, and this is a solid. So as you go down the periodic table, the molar mass increases. The number of electrons in these species is greater, and therefore the potential for a summation of these types of forces is greater, and the bond is a bit stronger. So London dispersion forces are very weak, by themselves, but actually can become quite large when you look at very large molecules that can have London dispersion forces over the entire surface. So just imagine you have a really large molecule. I'll just draw it like this rather than drawing something. And that you have London dispersion forces all along the surfaces here that can create a fairly large attraction. So the size of the molecule will be key. And you see it here beautifully just by the states of these. And here we're showing it in terms of boiling point. So things like boiling point and melting point are going to be affected by your intermolecular forces. And therefore, the state of the substance will be determined by these intermolecular forces at any given temperature. And viscosity is one of those other things that will be affected by these dispersion forces or intermolecular forces in general. So viscosity is just kind of resistance to flow. Okay, and you know viscous substances. You know that molasses is very viscous, and something like maybe cooking oil is less viscous, and water even less viscous. Well, the greater the forces, the more viscous, because for something to flow, the molecules have to slide past each other. And if they're coming entangled with each other due to forces, then they're going to flow much slower. So the size of the molecule, but also the shape, because sometimes we'll see this in class, excuse me, the shapes can interact as well with each other. The dispersion forces are minimized because of that shape, and therefore viscosity is reduced. That's just one of those things: viscosity, melting point, boiling point, and therefore the state of the matter, whether it's solid, liquid, or gas, are all dependent on these intermolecular forces. So the next type of force are these dipole-dipole interactions. They're going to be stronger than the London dispersion forces. And we've always used water, so we'll use water again. But I'll also use HCl here. Now, what will happen is, when I have these individual HCl molecules, remember, due to differences in electronegativity, this is more electronegative, has a partial negative, this has a partial positive, this has a partial negative, this has a partial positive. As a result, we have this partial negative attracted to that partial positive there. That's an intermolecular force. And that is a dipole-dipole interaction because we have these permanent dipoles. These over here, remember, are not permanent dipoles. They're temporary dipoles that manifest as a result of the proximity of individual species coming towards each other. These are permanent dipoles. If the HCl is isolated and all by itself in some sort of gas chamber, completely isolated, one molecule, it's still going to have that dipole due to the electronegativity differences. Now, that's a dipole-dipole interaction. If hydrogen is attached to either oxygen, fluorine, or nitrogen, due to their high electronegativity and small size, you get a special case of a dipole-dipole interaction called a hydrogen bond. So in this case now, when I have two water molecules attracted to each other, this bond here, these bonds here, these are hydrogen bonds. So if you will, all hydrogen bonds are dipole-dipole interactions, but not all dipole-dipole interactions are hydrogen bonds. Hydrogen bonds are a type of dipole-dipole interaction, and they're much stronger. So you would say, I mean, sometimes this is confusing the way SmartWork asks these questions. They'll say what type of forces are present, and they'll want you to say both dipole-dipole and hydrogen. And that's a little semantically confusing. I mean, I'm not sure I would agree with that. It's there's, this is a force here, and it's a hydrogen bond. Yes, it's a dipole-dipole interaction, but it's not a separate force. So just be aware of that if you're asked that, SmartWork or something. I'll avoid that type of confusion on any of my quizzes and exams. So hydrogen bonds are just a special case of dipole-dipole forces. Now, so as I've been mentioning all along, we see this influence on things like boiling point. And here's three species now, all with basically the same molar mass. So we can say that their London dispersion forces are basically the same. Because remember, we said London dispersion forces depend on the molar mass. And that's just a small difference. So we'll say that those are basically the same. But you look at the differences in boiling point. So something like ethane only has London dispersion forces. Formaldehyde has London dispersion and dipole-dipole forces. Methanol has the highest boiling point because it has the hydrogen bonding on top of those London dispersion and, if you will, dipole-dipole forces. So it's the strongest. Even though its dipole is less, because remember, a dipole is about the entire symmetry of the molecule. What I'm talking about here is saying this force right here of attraction is greater than this. It doesn't necessarily mean the dipole is greater, because the dipole depends on the whole symmetry of the molecule. So this has a greater dipole, but it has stronger, weaker intermolecular forces, and you can see that with the boiling point, and that's because of the strength of that intermolecular force. The boiling point is dependent on the strength of that intermolecular force. Okay, so now you can imagine, if we're talking about all these dipoles and charges, that species like ionic compounds would have charges would certainly interact with species that have dipoles, right? So water is going to certainly interact with this sodium chloride crystal. And that's how it dissolves it, basically. If we drop it in water, why does it dissolve? So what you'll notice is, if you were to look at it, each of the sodiums will be surrounded by waters. It's actually surrounded by 6 waters, but I'm not going to draw all of them. But you'll notice the oxygens are going to orient themselves towards the sodium, because the sodium's positively charged and the oxygens are negatively charged. The chlorine will be the opposite. The hydrogens will be oriented towards the chloride ion. Once again, that'll be surrounded by 6 waters. We just happen to know that's the size of the solvation sphere. So you got the sphere of hydration or sphere of solvation. Your book talks about that. This is how it's able to dissolve substances. So you might get the feeling now, as we move forward, that solubility will be in water will depend on its ability to interact with water. And ionic compounds will certainly have the capability of doing that. And so now that we've introduced these forces, here's an ion dipole force now that we just did. You can see the strength increases in this direction. And it's kind of like, okay, so you see that you got London dispersion, or just those kind of weak temporary ones that form. Then you've got a case where we didn't talk about, but you can have a dipole inducing a dipole in a substance that doesn't have a dipole. So imagine now something like water dissolved in, well, ethane's not a liquid. Ethane's a gas at room temperature. I'm trying to think of a solvent you might know that's non-polar. So think about that, something like a non-polar solvent. So I could say something like hexane. You don't know what hexane is. It's just 6 carbons. So it's an organic solvent. If I put water in there, that's a dipole. It can induce a dipole in some of the hexane molecules and be attracted. So here we're showing actually oxygen. Here's an example right there. It's oxygen gas dissolved in water. The water can induce a dipole in the oxygen gas. It's still going to be pretty weak, but because we have a permanent dipole here, it'll be a little bit stronger than the dispersion forces. Then you have your dipole-dipole, hydrogen bonding, and then ion dipole. So as I mentioned, some of these things, boiling point, physical properties, states of matter, this all depends on this. Now, you should remember what the solvent is and the solute. The solvent is the one that there's more of, and the solute, the one is less. Okay? So obviously, if I put some sodium chloride in a big amount of water, the solvent is water and the solute is the sodium chloride. And the solubility of a substance is the amount that dissolves. So there's limits to how much dissolves. And that's called your solubility limit, or the solubility of the compound. Well, we can start to see trends in solubility now. You might start to think about this is that, well, wait, if water is polar, that means that for something to dissolve in water, it should have to have, you know, some sort of polar interaction with water. Things like sodium chloride or maybe like methanol here, right? Right? That would be able to interact with water well because it has hydrogen bonds in that dipole. This would have dipole but this would not dissolve very well in water, you see? But two nonpolar substances, two hydrocarbons mix well together. So oil and water don't mix. When you think about oil, just think of a large hydrocarbon. This is a small hydrocarbon, but just keep adding those CH3 groups to it. And you have, octane when you have 8 carbons. The difference is the interior carbons will only have 2 hydrogens because of the bonding. When you draw it out, you'll realize that. So oil and water don't mix very well. And that's what you learned as a kid, right? Makes sense. There has to be, so polar like dissolves like. You know that phrase maybe. Not verse, dissolves. Like dissolves like. Polar substances dissolve in polar substances. Nonpolar dissolve in nonpolar. That is what this means. And you'll start to see this as we discuss it more in class. The last thing, well, not the last thing, the second to last thing are phase diagrams. I'm just going to introduce these. So what you typically have in a phase diagram is pressure on your y-axis. Could be in different units, but often atmospheres. Temperature on your x-axis in degrees C typically. And we have these lines that separate the different phases. Solid, liquid, and gas. Okay? And you have some key points on that. You have a critical point, which we'll talk about in class up here. You have a triple point down here. And then you also have your boiling points and melting points. And that would be normal boiling point and normal melting point, which is at 1 atmospheric of pressure. So this substance, you can tell, is actually water because 0 and 100 degrees C, that's water. Those are the normal boiling and melting points. Along the lines, both phases will exist in equilibrium, the solid and the liquid along here. At the triple point, all 3 phases exist. And you can look at what happens as you move across. Okay, it's a solid. I get enough heat and it melts to a liquid, then it turns to a gas, right? You can also change its state by changing the pressure, moving up and down. And the pressure affects whether it's a solid, a liquid, or gas. So just start looking at these phase diagrams and we'll talk about them more in class. Then the last part of my video then is just properties of water. And your book ends with this. Now, water's hydrogen bonding is what makes it really unique and a pretty important liquid. It's the liquid of the fluid of life. We really think about it. That's why we look for water on other planets. It's our sign of nothing we know of can live without water. But it's because it's so versatile. It has these unique properties. It has an unusually high boiling point for such a low mass. And that's because of the hydrogen bonding. This is all because of hydrogen bonding. It has a really high surface tension. It has a unique property in which the so I guess I should just say the surface tension is the ability of a surface of a liquid to resist forces against it. So the idea of a water strider moving across the surface of the water, or something staying on the surface of the water and not sinking, has to do with that surface tension of the water. Another unique thing you see in increasing the density of water as it gets colder. Also, with the solid being less dense than the liquid, that's unusual. Most substances, if you freeze them and drop them in their own liquid, will sink. Water, we know, floats. Also, it has the ability to flow against gravity. This is due to capillary action. So here's just some unique properties of water you can read about at the end of your chapter. We'll talk about them briefly in class. With that, I'm concluding your first video on Chapter 6.